Hello, this is Patrick O'Shaughnessy, and this is the third module in the series, Statistical Methods for Analyzing Data Obtained in the Lab or Field. We're going to focus in on simple linear regression in this module. So here's the map of modules in this grouping called linear regression and graphing, and you can see that it is advisable that you review the first module on graphing techniques before seeing this one, but it's not absolutely essential. You should be able to do okay if you understand graphing techniques already. Okay, so moving on to the terminology. So a model is obviously developed to predict the level of one variable based on the level of another variable. So that's the basic concept, and by one and one, that's what we mean by simple, is a one variable approach. This module will not consider multi-variables, multiple x's, so to speak, that will predict a single y. So the value that is predicted, that variable y that we use in all sorts of different types of models of this type, can be also referred to as the response variable, or maybe the outcome variable, and here the dependent variable. Meanwhile, the x is the predictor variable. It can also be called the regressor or the independent variable. So you can see x is independent because it is the thing that is driving the y that is dependent on the x. And then the model can be called a regression model or a linear statistical model. So all these terms can be used out there in the literature, as you'll see them here and there. Okay, so how are we going to go about a study in which we then apply these techniques? Well, there's two basic types. One is what you may consider as observational. You're going to, quote unquote, tweak the independent variable levels and then observe the dependent levels that occur because of that. You need to tweak them because you need at least two different independent levels in order to form a line right between the 2 points. So the tweaking is going to occur typically over 3, 4, 5, and perhaps many hundreds even of different levels of x in order to observe the dependent levels. In the very first module on descriptive statistics, some graphs were shown, say, of a time series and collection of data in which, yes, there were hundreds of values of occurring over time for which, say, a concentration of a pollutant were measured. So that is observational. You, in a sense, are going to have to be judicious about the way you tweak the independent levels, but you may also not even have that much control over it. You may be interested in the say the relationship between copper content of water and the viability of frogs in the pond. You're going to go out and take measurements of both at the same time. So you're not really tweaking anything in that case. You are coming up with associations as best you can given what nature has to offer you. A designed experiment, on the other hand, is where you have the ability to preset the levels of the x, of the independent variable, to be observed, and you can then say, I'm going to take or modify x 10 times and observe the y's that result from it. Another example from the first module was, say, having preset levels of the RPMs of a pump and then seeing what its output rate in gallons per minute is, for example. So it's more of a designed experiment. You have control over it pretty much entirely. You're not at the whim of nature as much as you would in an observational study. Okay, so given whichever way you're going about it, you're still going to have XY pairs. And again, if it's a single x versus a single y, it's referred to as simple linear regression. Multiple x's versus a single y is multiple linear regression. And it's just really, honestly, more of the same of what we will talk about in this module. Okay, now we need to discuss a little bit about the model assumptions. So first of all, we could assume that the relationship we have between the x's and the y's is perfectly linear. There's no randomness whatsoever. In that case, we could apply what's called a deterministic model to express x versus y in a linear fashion. And since high school algebra, we know what the relationship is in a mathematical sense. It's y equals b plus mx. That defines a straight line on graph paper, for example. You can get a little fancier about it in statistical terms. They refer to it as y equals beta naught plus beta 1x. This allows for the addition of additional x's, such as beta 2x2 plus beta 3x3, etc. That's where we get into multiple linear regression. That's the reason for the betas that are numbered. But this relationship, as we know, the slope is beta 1, gives a relative change in y for a change in x, a unit change in x. And beta naught is the intercept. It's the value of y at which the line intercepts the y-axis. So that's all well and good and known by most. Now, what if we go out in nature in the lab and we gather XY data pairs and we want to plot them and see whether or not they're linear? Typically, there's going to be some sort of random component to the collection itself that does not allow these points to fall specifically on a straight line. If that's the case, then there needs to be some component of the model that adds in this randomness, and it's what they refer to as a probabilistic or stochastic model then, which acknowledges the possibility that there is random variation in the data points about the model line. And so it looks like this, which is not much different from what we see above. You can see it's the deterministic model with an additional component tacked on, we call it this eta, which includes or incorporates the random variation. Okay, so now we have a probabilistic model, just taking a kind of a step up. And you'll see why this is necessary, because again, a best fit line implies that the best fit, of course, is one that goes straight through all the data points. But if all the data points are not lined up, then you have a best fit, again, that needs to be determined. And we'll get there in a minute or two. So the probabilistic model has two components, as we just discussed, a deterministic equation and this stochastic component, eta, to define the random variation of the actual data values. So there is the deterministic component, which gives a mean value of y for a given x, and then we have the random error tacked on. So this random error, to be specific about it, is basically what might be referred to as white noise. Each of the points, if you plotted them themselves, they would be independent. They would be normally distributed values, and they have a mean of 0, so they do not add to the height or depression of the line. They are literally points that are bouncing around the line because their mean is 0, and they have some standard deviation. Of course, the higher the standard deviation, the more they're bouncing around the line, so to speak. That can all be encapsulated into this notation right here that statisticians use. The capital N means that they're normally distributed with a mean of 0 and some standard deviation. So that is how we, again, get to a more sophisticated model. Okay, now we're going to discuss the method of least squares. This is going to get us towards a best fit line. So it is the method that's used to determine the values of both the slope and the intercept, beta naught and beta 1. Again, the goal is to minimize this overall difference between the measured value of y and the value of y associated with the regression line. So for example, over here, it is possible you could just do this by eye and just draw a line in that seems to do just that. You're actually pretty good at it optically, and you probably in that case would maybe try a variety of different lines, maybe one that goes through this point here, but then you would notice that the line would have a much bigger difference between this line or this point at 4, so that wouldn't work as well. So the same thing is going on mathematically to determine this line that minimizes these differences. So what do we mean by the differences? Well, let's just add a little point or a little line coming down right here and blow it up a bit. Okay, so there is going to be some space between the actual y value associated with an x, in this case, this x at point I, to the point on the regression line that is predicted by the deterministic model as shown there. So we call that y caret I. So the overall difference is the y that we have measured minus this y caret I. And you can expand it out as shown there, where you include the deterministic model as well. So the goal is to minimize all these differences. Now, if you tried a particular line, determine all the differences, added them all up, if you had the perfect one, ultimately those differences, because some are above the line, some are below, will add up to 0. So that's a problem, just like computing the variance as we came across in Module 1. So one way out of having a differences that add up to 0 is, you guessed it, to square the differences. So the formula now at the bottom is what is used to determine the best fit line by minimizing this, what they call the sum of the squared error. So the error is the difference between y and the deterministic model. There's y in the deterministic model, or y caret. But again, we're going to square it instead of just using the difference straight up. And then we're going to sum them all. So least squares is having the minimum of this sum of squared error, is one way to think about it. So now it's just a matter of trying to determine a method for mathematically getting at the sum of the square root of error that is minimized by the correct choice, so to speak, of beta naught and beta 1. Okay, let's get to that method as minimally as possible. So we have these equations to determine the values of beta naught and beta 1 are based on finding basically the root of the equations that relate each variable to this SSE. So the minimum value is found where the derivative is 0. So what does all that mean? If you chose a particular value of beta 1, say right here, and you then applied it to that equation to determine a line, you'll get the differences, you sum them all up and you square them, you may end up with a point right here in terms of the value of the SSE. Then we increase beta 1, and hey, the SSE is going down, so that's even a better selection than the previous one. And you see where I'm going with this. You will get to some sort of a minimum, and then you keep increasing beta 1, and your SSE is going to increase. So how do you find this minimum SSE, which is the minimum of the differences that we want? Well, you take the derivative of this curve, which is going to be a highly negative slope here, and it's ultimately going to go to 0 at this point right here. Right? So that's what we mean by a derivative is 0. And then, of course, there is some point where the derivative is exactly 0, and that will be the beta 1 we're after. Now, thankfully, there is someone solved the set of equations necessary to determine this minimum explicitly. There are explicit equations, means you just crank these equations, and every time it will solve for the slope and the intercept that guarantees the SSE will be minimized. So this is ideal, especially in the world of computers. So these formulas are a little different than perhaps you've ever seen before. because they have these notation here of capital S, X, Y. So the over S, X, X. That is how beta 1 is solved, and it will automatically be the minimum. There is, again, no doubt about it. There's nothing else that needs to be done. So what are those S's? They are also a type of difference squared, except the sums of the squares of the x's relative to the y's are, you can see, the x's minus their mean times the y's minus their mean, sum all those up, divided by the x's minus their mean squared. So it's kind of interesting to see that beta 1 is the ratio between these two summations of basically the variability of x's relative to y relative to the variation in the x's. That's one definition of a slope. Okay, so once you know beta 1, the minimum of it, you can then apply it to an equation consisting of x bar, the mean of x and the y, and the mean of y, and come up with what beta naught should be by back calculating that deterministic model equation for the intercept here. So now you've got them. And why do these have little carets above them, the beta 1s, beta naught? Because if I went out and did this one time in my system, I will end up with one set of slope and intercept. If I go back the next day and do it again, I most likely will not get exactly the same beta 1 and beta naught. Just like going out in your system and getting an average one day, and you're going to get another average the next day and another average the next day. It's the same thing here. So they are statistics, as we described in the previous module. Okay, using Excel. Let's say we have 5 specimens for which we apply some known pressure, and we're looking at some resulting measure of compression. And we have just some simple numbers here to delineate those. We go and put them into Excel, create a chart, an XY chart specifically, that has just markers on it. You can then right click in that area and ask to add the trend line, and the trend line will be automatically put in. Again, it's utilizing those equations for the sums of the squares of the x's and the y's, etc. And again, it falls into place every time mathematically. The format trend line feature will come up, defaults to linear over here, but other types of models can be applied to the regression. And then down at the bottom, it says display equation on the chart. That is not clicked. That is not a default. You have to click on it to get the equation to show up. Same thing with what's called R squared, as we'll talk about. That also has to be clicked on to show it here. So that is the basic and very simple way of getting a regression line through data points in Excel. Okay, there's one more step we can do here. Now that we have the data analysis tool pack, and again, you have to go back to module 1 to see how it's downloaded into your computer, because it's not available by default in Excel. And once it is available, then you would click on data, data analysis, and then choose the regression function, and up pops this regression box right here, in which you first put in the Y range. And so you would click on the Y values, then click on the X values. You can check a confidence interval if you'd like. You check output range, then go to this little up arrow, click on it, and then come to your sheet and say click on a cell such as A10 here, and then hit OK, and it will immediately put all this information into Excel for you. So you not only have the regression equation in the graph itself, you now have actually the slope and intercept down here as a number with 32 digits. Now, these just happen to be 0.7 and 0.1. as values, so nothing fancy there, but this is one of the good things of having information. If you need to then use the slope and intercept as a model, you would want all the digits available to it. And we'll talk about the rest of this information as we go on here.